Okay, so what we're going to do now is continue with more theorems, namely all kinds of convergence tests. And the most of them are going to be in the context of positive series. So we're going to restrict our discussion to positive series for a while and have some results which only relate to positive series. By a positive series, I mean a series that sums a sequence of which all the elements are positive. Sometimes we can allow non-negative, but in general, that's what I mean by a positive series. And why did these have more theorems related to them? What's nice about them? So the answer is, if sigma ak is a positive series, meaning that ak is greater than 0 for every k, then what can you say about Sn, the sequence of the partial sums? It's also positive, that's true, but can you say something deeper? It's monotone. Monotone what? Increasing. Sn is monotone increasing. Because when n gets bigger, you're adding more things. So it always gets bigger. So monotone increasing. So strictly depends if we allow ak to be greater than or equal to 0 or not. But that's not the important issue. If we have an increasing sequence, Sn is an increasing sequence, what do we know about its convergence? Exactly. If it's bounded, it converges. That was a theorem for sequences. Any monotone bounded sequence converges. And if it's not bounded, diverges in a very specific sense. It goes to infinity. Do you agree? So Sn is monotone increasing, and hence the limit of Sn equals some finite L if Sn is bounded, and infinity if not. And those are the only two cases. We can't have situations like -1, 1, -1, 1, where the sequence of partial sums diverged, but just because it bounced back and forth. Clear?
Is it a theorem or?
This, you can call this a theorem. This is kind of like observations. Observations on positive series. Okay? So, when we want to study whether a positive series converges, we don't need to actually calculate the limit of the Sns. All we need to do is determine whether they're bounded. If they're bounded, they converge and we're done. Do you agree? Okay, so a positive, so the conclusion is a positive series converges if and only if Sn is bounded.
Okay.
Yes?
Let's say the upper one for Sn is 10.
Mm-hmm.
From some after a value, it's between 9 and 10. But 9 times infinity is infinity. It's not bounded. It's not
I don't understand your question.
We say that the limit
Sn is the sequence of the partial sums. It's not just any sequence. It's a sequence of the partial sums of the series. Okay? You keep adding. Sn is the sum of the first n terms in the partial sum.
Yes, if the terms are between
not the terms, they're sums. Not the ANs, the SNs. So, okay, I don't understand your question. Try again.
Sn is AK1, like A1 plus A2 plus A3 is like that, right?
Right. SN is A1 plus A2 all the way up to AN.
Okay. If AK is between 9 and 10, it's bounded.
SN? No, if the AKs are all between 9 and 10, SN is not going to be bounded. Because you're always adding 9 or 10 or whatnot. You're getting bigger and bigger. You're confusing the sequence itself with the sequence of the partial sums. Okay, I can see you're still not there. Sn is the sum of the first n elements. In order for this sequence to be bounded, which is if and only if it converges, the ANs have to go to 0. That was the previous theorem. Okay? If the ANs don't go to 0, you're adding something every time. The SNs are going to get bigger and bigger and bigger, and they're not bounded. And in particular, they don't have a limit, or their limit is infinity, and therefore this diverges. Good? Yep. Okay. So a positive series converges if and only if Sn is bounded. Sn, not An. An has to go to 0 for it to converge. And that's not an if and only if statement. That's only an only if statement. It's a one-directional statement. Okay. So let's do some examples. Yeah. So the role played by this observation is actually in the proofs of the theorems that are going to come. And we're not going to prove all of them. Maybe we'll do one or two as examples. Okay, so I want to write an example which kind of motivates the next theorem. And the example is the following. Remember that we had the fact that the sum k equals 1 to infinity of 1 over k plus 1 converges. This we already know. Remember how we proved this? We broke it into partial sums and then did a telescope argument. Remember this? Okay. By the way, what example number are we on? I lost count. 9? Okay. So this we know. This we know. Do you agree that this, so I'm going to write it before I actually write the example that I want to work on. I want to write this in a different way, and the first time you see this it may be confusing. This is the same as k equals 2 to infinity, 1 over k minus 1 times k. Do you agree that this and this are precisely the same thing? It's kind of an index shift. The way to be convinced, if writing it in summation notation confuses you, the way to be convinced is to just spell out the elements. The elements here, the first element is you plug in k equals 1. So you get 1 over 1 times 2. The next element is 1 over 2 times 3. Then 1 over 3 times 4. Right? What are the elements here? The first element is when k equals 2. So it's 1 over 2 minus 1, which is 1 times 2, just like the first element here. The second element is 1 over 2 times 3. Do you see that? So do you agree that this and this are precisely the same series? Everybody? Okay. So what I want to argue now is the following argument. So this converges because it's precisely the same thing. Since this converges, and it's a positive series, all the elements here are positive, all the elements of the sequence, we know, so this converges, and it's positive. this means that the sequence of partial sums of this thing is bounded. That's this statement. So if I write sum k equals 2, not to infinity, but to n of 1 over k minus 1 times k, this is Sn. This thing is bounded. So this is less than or equal to some m, some number, and this is true for any n. Do you agree to this? I just exploited this fact. Clear? I can see some people here are confused. I don't know why.
Where did the M
And you're not asking.
Where did the M come from?
The M came from here, from the marker.
Where did the marker come from?
My hand. No. What does it mean that a sequence is bounded? It means there's an upper bound. Right? That's the M. But this is true no matter what n is. 5, 17, 1 million, same M. It's a bounded sequence. Question?
Yes. Why did we have to convert the series from k equals 1 to infinity to k equals 2?
Well, I didn't tell you what I'm trying to show yet.
I thought you just did that in order to be bounded.
No. I'm building up towards something, but I didn't tell you what that something is yet. I started with something we already know. I converted it to this. You'll see why in a minute. And then I'm claiming this. Good? Okay. So now what I want to say is the following. 1 over k squared is less than or equal to 1 over k minus 1 times k. And this is true for any k. Why is this true, by the way? Because here the denominator is smaller, so the fraction is bigger, right? But this is only true for k's which are greater than or equal to 2. If k is 1, there's an annoying 0 here, and I can't write this. Do you agree? So this is another fact. So this is true for any k greater than 2. Therefore, if I sum n of these, it's going to be less than or equal to if I sum n of these, because each one is bigger. So the sum k equals 1 to n of 1 over k squared is less than or equal to the sum k equals 1 to n of 1 over k minus 1, but I have to correct, not 1, 2. I can't write it for 1, because for 1 there's something going wrong here.
Which is less than.
Do you agree? Good, good. That's the next step. Do you agree to this? And this, we know, that's the previous line. This is less than some m. Less than or equal, we wrote, doesn't matter. For any n. Do you agree? So what we just found out, that this sequence of partial sums, which is the sequence of partial sums for which series? 1 over k squared, is bounded. But if this thing, we can't call it Sn because we call this Sn, so let's call it Tn. So it's the sequence of partial sums for the series 1 over k squared. And it's bounded. But if it's bounded, the series converges. So, conclusion, let's move on to the next board. The sum k equals 2 to infinity of 1 over k squared converges. Because its sequence of partial sums is bounded, and it's positive. And if it converges when k goes from 2 to infinity, then of course if you throw in one extra additive factor at the beginning, it would still converge. And that's what I wanted to prove. This was example 9. Clear?
Why did we need all that to prove that?
That's not all that. I claim that we worked very, very, very easily to prove this. We didn't calculate the limit of the partial sums. We only made some boundedness argument and got it for free. Calculating the limit is easy. If I remember, there's the limit is something like pi squared over 6. It's surprising. And we didn't do it. We really did an elegant detour and got it really, not for free, but for almost free. Yes?
How can we say that the series from K equals 1?
What is this thing? This is just 1 over 1 squared, 1 plus this thing. If this thing converges and you add 1, it will still converge. Right? Okay? Okay, so this is what I wanted to show in this example, that we actually got convergence of a sequence, of a series, without calculating the limit of the partial sums, just by arguing that they're bounded. And we did it by, let's say the actual word, by comparing to a different series which we already know converges because it was telescopic. And that's what I want to make more general now by writing the comparison tests for series. Okay, so theorem. And of course it's going to resemble the comparison test for integrals. So if bk is greater than or equal to ak is greater than or equal to 0 for any k, then, so this is the statement of the comparison at the level of the sequences. Just like in the integral version, the comparison was at the level of the function. And the conclusion, then, sum bk converges implies sum ak converges. If the bigger one, when you sum it, converges, so does the smaller one. Okay?
Like we can connect it to the sandwich theorem or something?
No, this is precisely the comparison test. I forgot to write it. It's precisely the comparison test. Comparison test, or the direct comparison test, it's sometimes called, because there's also the limit comparison test, which we'll write in a second. And let me remind you that this is 2 for the price of 1 sale. If you know that sigma ak diverges, then of course that implies that sigma bk diverges as well. Okay, because if this diverges, if this were to converge, it would imply this converges. But if this diverges, then this must diverge as well. Yes, question?
Say without loss of generality for negative series?
So the way I stated it, and in fact the entire discussion now is for positive series. In this specific one, if both of them are all negative, so not alternating, but all the elements are negative, then you can, of course, do this. You can just pull out a minus sign and do the argument at the positive level. Do you see that it's the same, that it really resembles the comparison test for improper integrals? Do you see that? Okay. So here's an example, example 10. So, so example 10, if I have sum of 1 over k to the power 3, what can you say? So this thing converges. Since 1 over k to the power 3 is less than or equal 1 over k squared. Do you agree? This is for, and non-negative, of course, important. And this is for any k greater than or equal to 1. Do you agree? Since this is true, therefore, sigma 1 over k cubed converges, since sigma 1 over k squared converges. This we know by the previous example. So by the comparison test. Good? I wrote it in a funny way. I wrote this converges, so let's write it like this. Since this, therefore, forget the since. We know this for every k greater than or equal to 1. Therefore, this converges since this converges. Good? Yes?
Whenever we have a sigma with no notation around it, can we just take it as k equals 1 to infinity?
Right. This is being sloppy. You should write k equals 1 to infinity. And if I forgot to write it, and if it's evident from the context, then yeah, it's a k equals 1 to infinity.
If we forget to write it, say, in an exam...
But try not to forget to write it. Don't ask me to legitimize forgetting to write it. Try to remember to write it. Okay? That's the... Because it could be confusing. You could be looking at partial sums, and then there would be an n up here. Try not to forget. Okay? And since I've been called to order, then I will write it. Okay? Example 11. So, sum of 1 over root k. K equals 1 to infinity. So, 1 over root k is greater than or equal 1 over k, which is greater than or equal to 0 for every k. Do you agree? Not true?
Why is it greater?
Oh, k greater than or equal to 1. K's are integers. So if you take the root, it's smaller than the number itself. 1 over it is bigger. Good? Okay. And so sigma 1 over k diverges. This we didn't prove yet. We're going to prove it. Okay? So this little fact we didn't prove yet. But let's believe it for a minute. Therefore, sigma 1 over root k diverges by the comparison test. By the comparison test. Good?
But to say that in an exam or something, we need to prove that 1 over k diverges.
I said we're going to prove this. We're going to prove this fact. Okay? I'm postponing it for a while because I want to use a specific tool to prove it.
No,
But
asking on an exam, is it enough that we proved it in class? We could just say 1 over k.
Right. On an exam, you can use anything we already proved in class. Not a specific example, but we're going to prove in general sigma 1 over k to the power alpha. Okay, and we're in fact going to see that they behave just like the integrals of 1 over x to the power alpha. And that's what I want to use to prove it. It's going to be a theorem called the integral test. Okay, that's why I'm postponing it. But you can quote this fact and this fact and this fact. Those are all known facts, and they're one specific theorem that's going to show up in a few minutes. I haven't defined what a few is yet, but good? Okay, so just so everybody is completely relaxed and calm, we will prove, we will shortly prove that sigma 1 over k to the power alpha, k equals 1 to infinity, converges if and only if alpha is greater than 1. Okay? We will prove this. Everybody calm? Relaxed? Good. Okay. Okay. Good. Good. Okay. So this was the comparison test. I thought of maybe proving it, but in fact, the proof of the comparison test, the proof of this, is really just generalizing the idea that we did in the example that preceded it. Okay? Let me just say it and not write it, and you can try filling in the details. If sigma bk converges, listen here and tell me if you can follow, just saying it. If sigma bk converges, the partial sums of the bk's are bounded. If their partial sums are bounded and the ak's are smaller, then whatever the bound is for the partial sums of the bk's will be a bound for the partial sums of the ak's, because these are smaller sums. And therefore the partial sums of the ak's are bounded, sigma ak converges. That's the proof. That's all there is to it. Good? Everybody? Okay, so you can write it down. It's precisely what we argued in the example that preceded this test. Okay, so let's write so this is sometimes called the direct comparison test in order to tell it apart from the limit comparison test, which is also not going to surprise you because you've seen its version for integrals as well. So the limit comparison test it's a theorem. Yup. Wow, you're not relaxed today, huh? Well, what could it be? Could it be an apple? A theorem. Okay. So, remember, we're only dealing with positive series throughout. Until this title goes away, we're only dealing with positive series. So, if L is between 0 and infinity, and the limit as k goes to infinity of ak over bk equals L, then sigma ak and sigma bk diverge/converge together. So either both converge or both diverge. Okay? Let's do examples. But maybe before the examples, let me write a remark. I don't even remember if I wrote this remark for the improper integral version of this test, but the remark is valid there as well. So remark, if L equals 0, then sigma b, which one was the, yeah, sigma bk converges implies sigma ak converges, but no longer if and only if. So if L is 0, you only get one direction, whereas if L is strictly between 0 and infinity, you get an if and only if statement. And if L equals infinity, then you also get a one direction statement, but the other direction. So sigma Bn diverges implies sigma an. Why did I move to n's? AK diverges. Good? Okay, so let's do some examples. Example number, what? 12, I guess. Sigma 1 over root 3k squared plus 1. So before I try using theorems on it, whatever convergence tests, let's think about it. Let's try to intuitively understand what's going on. When k's are very big, and we're looking at a limit phenomenon, so k's get very big, this 1 becomes totally negligible. Do you agree? So, and this 3 is just a constant. It can't impact convergence or not, right? It can impact the sum, but not whether it converges or not. So this behaves like, and this is only an intuitive statement, this behaves like 1 over the root of k squared, which is 1 over k. Do you agree? Do you see where that intuition stems from? Everybody? How do I formalize it? So maybe let's write it. Intuitively behaves like sum of 1 over k, which diverges. We're going to prove that shortly. Don't worry. So how do I formalize this? Here's the formal proof. 1 over root 3k squared plus 1 divided by 1 over k. I want to take the limit of the quotient as k goes to infinity. So what do I get here? I can multiply by the reciprocal, so I get a k up here, and then I can throw it under the root, so I get the root of k squared over 3k squared plus 1. I can divide top and bottom by k squared now, so I get the root of 1 over 3 plus 1 over k squared. And when k goes to infinity, this goes to 0, so this goes to 1 over root 3. I don't care about this precise value. All I care about that it's between 0 and infinity. Therefore, so by the limit comparison test with sigma 1 over k, that's what I'm comparing to, this diverges. This diverges. Good? I compared the sequences, the quotient of the sequences, AK over BK, has a finite limit. Therefore, this converges if and only if this converges. We know that this diverges, therefore this diverges. Question?
If we take instead of the sum of 1 over k, the sum of 1 over k squared, we would have gotten the limit equals to 0. In that case,
We can check the calculations, but no. I'm so confident that I'm willing to say that no, without checking it. Do you want to check it together?
the root of k over 4.
So you're saying, what if we took k squared here?
Yeah, so we have
Then you would have k over 4 here.
infinity, I'm sorry.
Infinity.
Yeah.
Right.
And
And
so
so,
it diverges.
if sigma b, which is bk? Yeah. So you'd gotten the same thing. No, 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 no. Sorry, sorry, sorry. Then you wouldn't get an answer. It wouldn't solve it. Right? You would get the limit to be infinity, but in the infinity case, all you know is that if this diverges, then this diverges. But your bk's are now sigma 1 over k squared. That was your suggestion, to take 1 over k squared here. That converges, so you get no statement. It's no longer an if and only if statement. Okay? Good observation. Good question. More questions? Okay. Good. Okay. What I want to write now is 2 more convergence tests. 2 more. And these do not have counterparts in integrals. These are really series-oriented only. Theorem. For you, theorem. So this is called the ratio test. Also named after a mathematician, D'Alembert. It's an E?
We hate him as a class.
You hate him as a class?
Yes, I'm glad that he died.
Oh my God! This has just been recorded. I would not repeat that. Hopefully the microphone didn't pick it up. So, again, we're still in the and let's get serious here. We're still in the context of only positive series. Only positive series. So, sigma ak positive. It's not on this board, so I am emphasizing this. If the limit as k goes to infinity, now look what the limit is looking at. It's not comparing to a different series. It's taking a limit of ratios of elements of the sequence itself. ak plus 1 divided by ak. If this limit equals some, let's call it q for quotient, then q is greater than 1 implies sigma ak diverges. And q is less than 1 implies sigma ak converges. And let me write q equals 1, we don't know. So there's no statement. Both can happen if you found out that q equals 1, or that there's no limit or whatever, you just can't use this test. Okay? Let's do an example, or some examples. By the way, there's a ratio test, not for series, but for sequences. And I don't think we mentioned it when we talked about sequences. It doesn't play such a significant role, whereas in series it does. But just so you know it exists, and you can look it up if you need it. It's very similar to this. Okay, so example what? 13. Let's look at sum 2 to the power k divided by k factorial. This is when you see factorials, that's when the ratio test is the ultimate tool, when you see factorials. So I'm going to use the ratio test. First, I note that this is a positive series, so I can use it. And now I'm going to take the limit as k goes to infinity of the k plus first element, which is 2 to the power k plus 1, divided by k plus 1 factorial. over the kth element. Instead of writing the kth element in the denominator, I'm going to multiply by its reciprocal. Can I do that right away? So I'm going to multiply by k factorial over 2 to the k. Do you agree that this is ak plus 1 divided by ak? Everybody? Okay. Now, so let's see the beautiful cancellations here. So 2 to the k cancels with 2 to the k plus 1, leaving just 2. So I'm going to do this not so formal writing, but you understand what I mean. What about k factorial and k plus 1 factorial? Right, so I'm going to cancel k factorial with exclamation mark here. So what I get, don't do this on exams, please. Okay, just write an extra step. Limit k goes to infinity of 2 over k plus 1. And what's the limit? The limit is 0. What do I care? What is the property of 0 that I'm interested in right now? It's less than 1. That's the only thing I care about now. And therefore, the series converges by our beloved D'Alembert, which I don't know if I'm spelling correctly. And I'm not going to ask where you encountered him and why you hate him so much. Okay, another example. Sigma 2 to the power k over k. So again, I'm going to do the same sort of calculation. Limit k goes to infinity. 2 to the k plus 1 over k plus 1, multiplying by the reciprocal, k over 2 to the k. These cancel, leaving just a 2, so I get the limit of what? 2k over k plus 1. Dividing top and bottom by k, I get 2 over 1 over k plus, I'll just write it. Limit k goes to infinity, 2 over 1 plus 1 over k. And what's the limit? 2. What's the property of 2 I care about right now? Greater than 1. Therefore, converges, diverges, you're right, sorry. Diverges by D'Alembert. Good? I want to make a remark here. Here, we found out that this thing converges using the ratio test. Okay? Here, we found out that this thing diverges using the ratio test. But if you take a step back and look at it again, it's very easy to see that the sequence we're summing here does not go to 0. Do you see that? This thing didn't even stand a chance to start with. We didn't really need this ratio test. We could have right away said, hey, this sequence doesn't go to 0, this diverges automatically. By the most basic reason. Okay? Do you see that? That's always going to be the case with the ratio test. If the ratio test picks up a diverging series, it's because the sequence doesn't even go to 0. Maybe I'll write that as a remark. If sigma ak diverges, not in general, but if it diverges by the ratio test, then ak does not go to 0. Okay, we're going to use this fact later. That's why I'm mentioning it.
Can you say it again? I didn't understand why.
I didn't prove it. You can...
Intuition, I'm asking.
That's the statement. If you picked up a diverging series by the ratio test, then the sequence doesn't go to 0.
Isn't that like the ratio test for sequences?
No, I'm talking about series. Okay? Everything is behind the scenes related to the ratio test for sequences, but I don't want to get into that corner right now. Okay? So you can actually see this. This fact is crystal clear in the proof. I just don't want to go into the details of proving the ratio test. Okay? Okay. 5 more minutes and then our break. And I'm going to be lazy right now. So, theorem. Instead of ratio test, I'm erasing the word ratio, and I'm going to write the word root. Root test. And I'm going to erase D'Alembert, which will make you happy for some reason, and write Cauchy. Sigma AK positive. And now instead of looking at ratios, I'm going to look at roots. Kth root of AK. And everything else remains the same. So take a minute to copy this. I'll erase the board in the meantime. Everybody finish copying the root test? Okay, if you're at home, press pause. Okay, examples. Oh, back to black. Example number 15. Suppose we want to look at the sum k equals 1 to infinity 1 over ln of k to the power k. When you see a power, it's kind of suggesting let's use the root test. So the kth root of 1 over ln of k to the power k equals the kth root of 1, which is what? 1, over the kth root of blah to the k. That's just blah, which happens to be ln of k in this context. Right? When k goes to infinity, what does this go to? 0. What's an important property of 0? Less than 1. Therefore, this thing converges by the root test. Good? Another example. Example 16. Let's look at sigma 2 to the k over k squared. So again, let's look at the kth root of 2 to the k over k squared. This equals, the kth root of 2 to the k is just 2. The kth root of k squared is the kth root of k squared. As k goes to infinity, what does the kth root of k go to? 1. So this entire thing goes to 2, which is greater than 1. Therefore, this thing diverges by the root test.
Would it be sufficient proof to just say that 2 to the k is an exponential function and k squared is a polynomial? Therefore, the exponential function always...
It would be sufficient, and that would have been my next remark, to say, hey, the sequence doesn't go to 0. An exponent over a polynomial where the base is greater than 1, 2 to the k over k squared goes to infinity, not to 0. Therefore, this thing diverges. Okay? Straightforward observation. And the same remark that we had previously. So let's rewrite this remark here. Note, instead of what's the minimum stuff I have to erase? I have to erase this and the A. If sigma AK diverges by the root test, then AK doesn't go to 0. Okay, same remark as we had for the ratio test would hold for the root test. Again, it's hidden in the proof. But we're not writing the proof, so you're just going to have to believe me on that, and we're going to use this fact. Question, yes?
If you would get that Q equals 1, then what's your next step?
Okay, so the question was, what if Q equals 1? If Q equals 1, we don't know. This test just doesn't say anything. Okay? You need to use something else. You need to resort to a different test. Either the comparison tests, or the integral test, which we'll see after the break, or other stuff. Okay, we're not going over all possible tests in this course. Okay, there are some very powerful ones also for integrals, which we're not mentioning. We're only doing kind of introductory level things here. Okay, so for example, if you would try to prove that sigma 1 over k converges or diverges using this, or the ratio test, in both you would get Q to be 1. So sigma 1 over k is still a mystery. We still have to wait for after the break to see the integral test to prove it. Okay, so let's have a 10-minute break now.